and electron will become free and electron will leave a vacancy, and that vacancy is known as the hole. Okay. So we did this. So I think I have written, from the next class this we will have to discuss. So first we will revise again, no problem. At absolute zero temperature, the electrons, there are no free electrons, as all the electrons are involved in the covalent bond formation. Okay, a semiconductor behaves as insulator at 0 Kelvin. On increasing the temperature, more and more thermal energy is available. Some covalent bonds may break and some electrons are generated and equal number of holes are also generated. Okay. So now
Equal
we will
number
see
of
the,
holes.
yeah, because you can see here when this bond will broken, this
Yeah.
electron from here, for
Yeah.
example, this electron is becoming free.
Yeah.
So here the electron will leave a vacancy. So
Yeah.
a vacancy is created. A vacancy is created, and that vacancy is known as hole.
Okay.
Basically, hole is a concept to explain the conductivity of a semiconductor.
Okay.
So I told you in the last class that at 300 Kelvin or 227 degrees centigrade or room temperature, this is a room temperature, one covalent bond in 10 to the power 29 atom will break. Means at room temperature also very few covalent bond will be broken.
Yes, sir.
Okay. And when the covalent bond will broken, I told you what will happen. Suppose this covalent bond broken. So the electron, this is the electron, this red color is the electron, this is the hole. Suppose this bond has broken. So this bond has broken. So what will happen? The electron will become free and it will leave a vacancy that is known as hole. And hole is having a positively charged. Hole is having positively charged. Now point number third. From here we will start. Number of thermally generated electrons are equal to number of holes. Is it true or not? True, na?
Yeah.
Okay. So number of electrons generated, these are the number of electrons we are taking per unit volume, because there will be millions and trillions of electrons, So we cannot just take exact number. So we will calculate the number of electrons and number of holes per unit volume. In a unit volume, how many electrons or holes are there? So basically, number of electron, number of holes will be equal in case of the intrinsic semiconductor.
Yeah.
Number of electrons and number of holes are equal in case of the intrinsic semiconductor, and these numbers are per unit volume. Okay, so this is true for intrinsic semiconductor. And what is Ni? Ni is representing the intrinsic charge carrier. Intrinsic charge carrier. Intrinsic charge carrier. Intrinsic charge carrier density. Okay. Or charge carrier per unit volume also you can say. So at room temperature, it is found that number of intrinsic charge carrier in case of the germanium is 2.4 into 10 to the power 19 per meter cube. And for silicon, this number is 1.5 into 10 to the power 16 per meter cube. These are the number of charge carriers. And this is the relation between the temperature and the intrinsic charge carrier. Ni is directly proportional to e to the power. This e is the exponential function. So e to the power minus eg divided by et. And eg is what? Energy gap, energy band gap. Forbidden energy gap, you can say. K is known as the Boltzmann constant. T is the absolute temperature. And when you will plot the graph, this type of graph we will get. Okay, with temperature, the number of intrinsic charge carriers are increasing. Okay, this is T1. Suppose this is N1. So when you will again increase the temperature, you will get again N2. So you can say T2 is greater than T1. So N2 is greater than N1. Now, what types of charge carriers do semiconductors have? Number one, free electrons. Number two, holes. So electrical conductivity of semiconductor will be due to the electrons and holes. Point number 4, current in semiconductor is due to thermally generated free electrons and holes. Thermally generated free electrons and holes. Okay. Thermally generated free electrons and holes. Now current due to electrons, if suppose the electric field is in this direction, and so what will happen? Electron will move in this direction. Electron will move opposite to the electric field.
Yeah.
Because electron is negatively charged, so current will be in the opposite direction of the motion of electron. So current due to electrons will be suppose in this direction. So current due to hole. So holes apparently move in the direction of the applied electric field. Holes apparently move in the direction of the applied field. So this point you can understand with this example. This is a silicon crystal. And what will happen? Suppose you have given some of the energy, you have applied the electric field. So the neighboring electron means this electron will move from here and occupy the hole.
Yeah.
Occupy the hole.
Yes.
Because what I told you that initially at thermal means at room temperature there will be some electrons, there will be some holes. Suppose this is the hole at the room temperature, and you have given small energy, some of the energy you have given or you have applied the electric field. So what will happen? The free electrons, this bounded electron will occupy the hole. This boundary electron will occupy the hole,
Yes.
and this hole will occupy this position, and here will be new hole created. So here you can see a new hole is created. So in this way there will be the formation of holes. In this way there will be the formation of hole in the crystal. See what is happening here. I told you that at room temperature, there will be some few electrons, few free electrons, and few holes are there. So this is the case I have taken at the room temperature. So at room temperature, suppose this is the hole. This hole will accept one electron, or you can say the electron will go into this hole. Okay, the neighboring electron will occupy this hole when you will apply the electric field, because electric field is in this direction. So on this electron the force will be in this direction, so this electron will occupy this hole, and here electron now is removed from here, so here a new vacancy is created, and that vacancy is this vacancy. So now that's how there will be the formation of hole. So electric field applied in this direction, and I told you that hole is a positive hole is having a positive charge. Okay.
Yeah.
So this hole holes are moving. First hole is here, now hole is here. So holes are moving like this in this direction. In the direction of the electric field, the holes are moving. So here, this is a hole.
Yeah.
This is moving in the direction of the electric field, and hole is a positive charge, and direction of the positive charge is direction of the current. So current due to hole will be in this direction, and current due to electron also will be in this direction. Both current will be in the same direction. Now with the help of energy band, we can also explain this phenomena. In this is the condition at the room temperature. At this is conduction band, this is valence band. So at room temperature there will be few electrons in conduction band. There will be few electrons in conduction band due to the breaking of the covalent bond. So due to these electrons there will be the current in this direction. If you have applied the electric field in this direction, okay, so current due to these electrons will be in this direction. Okay, after that what will happen? Now these holes are created at room temperature. So these electrons, other electrons in the valence band will occupy the position of the hole. You can see here. This electron is this is the valence electron or boundary electron. This electron will be in the valence band, so it will occupy the whole position. So here you can see occupying the whole position. Now here new holes are created. Okay. Now these electrons will occupy the position of the hole. Here new holes are created. So you can see holes are moving in the direction of the
magnet.
No.
Electric
In the
field.
direction of the electric field.
Yeah, electric.
So current due to hole will be in this direction. So net current will be due to the electron and due to hole. So IE is the current due to electron due to thermally generated free electron. IH due to apparent motion of holes or actual motion of valence band electron.
Hmm.
Actually, now what is happening? Holes are not moving. Actually, the holes are not moving. That the moving is the valence band electron. Valence band electron is moving, not the hole. You can see this is the valence band electron.
Yeah.
Boundary electron is a valence band electron, and
Yes.
this is moving.
Okay.
And holes are just appearing to move.
Okay.
Because due to the motion of this electron, the holes are creating.
Okay.
Now you can see here, current due to electron is not equal to the current due to hole. Okay, this we can see with this. I is equal to A N E V D. Current is equal to A area and number of charge carrier per unit volume is the charge on electron. VD is the drift velocity. In case of the semiconductors, intrinsic semiconductor, number of holes and number of electrons are equal. So this value is equal.
Okay.
Same for both. Okay. Now electrons, free electrons are in conduction band and holes are in valence band. So the mobility of electrons in conduction band will be more as compared to the holes in the valence band. So that is why the current due to electron is more as compared to the hole. So here I have written IE is the current due to the electron in the conduction band which are free to move. So IE is the current due to electron in conduction band which is free to move, and due to hole, current due to hole is due to the electrons in valence band basically which are not so free to move. Actually here the conduction band electrons are moving, holes are not moving.
Yeah.
But these conduction band electrons are bonded electrons, so they will have less mobility as compared to the electrons which are present in the conduction band. Valence band electron have less mobility as compared to the conduction band electron. So this is the intrinsic semiconductor. Now we will discuss the extrinsic semiconductor. So in case of the extrinsic semiconductor, what we will do, we will take one intrinsic semiconductor and we will add impurities. Impurities means atoms, different atoms we will add.
Okay.
So extrinsic semiconductor. Now, why there is a requirement of extrinsic semiconductor? Because the conductivity of intrinsic semiconductor at room temperature also is very less. So that is why there is a requirement of extrinsic semiconductor. So the electrical conductivity of intrinsic semiconductors increases with temperature. Which I told you, even on reaching the room temperature, its conductivity is very poor. The addition of certain impurities can increase the conductivity of intrinsic or pure semiconductor.
Okay.
If you will add the impurities to the extrinsic semiconductor, then
intrinsic, right?
Intrinsic. When we will add the impurities to the intrinsic semiconductor, its conductivity will increase. Now here is the data. Very small amount,
Parts per million.
part per million of impurity atom can increase the conductivity of intrinsic semiconductor many times. Okay, here is the example. One atom of impurity in 10 to the power 8 pure atoms of germanium increases the conductivity of pure germanium 16 times. So basically, what are the extrinsic semiconductors? The semiconductor obtained obtained after adding impurity to pure semiconductor are extrinsic semiconductor. Is you can say
Hmm.
are extrinsic semiconductors. And the process of doping, or the process of adding impurities is called doping.
Okay.
Okay. The impurity atom, is called dopant, and the impure semiconductor form is known as doped semiconductor. So, understanding now what is happening here.
Yeah.
What is the extrinsic semiconductor?
Impurities are being added.
Addition of impurity is known as doping.
Yeah. And
So
the
doping,
conductor is called doped conductor.
dopant
Dopant.
means the impurity which we are adding is
Yeah.
called dopant.
Okay.
So now we will discuss the how impurities can be added.
Okay.
So doping can be done in many ways. Number one, heating pure semiconductor in atmosphere of impurity atom so that impurity atom diffuse in pure semiconductor. So first method is that take the semiconductor, pure
Yeah.
semiconductor, add, sorry, take the extrinsic semiconductor and intrinsic semiconductor and heat
Yeah.
this semiconductor, but the environment here
Yeah.
around it,
Yeah.
or the particles or atoms which are surrounding this intrinsic semiconductor to which you are heating
Yes.
should be of impurity. So what will happen when you will heat it? Diffusion will take place,
Yeah.
and in this way you can add the impurity to the intrinsic semiconductor. Another way is bombarding pure crystal with ions of impurity atom. Take ions of impurity atom and bombard on the intrinsic semiconductor.
Okay.
In this way also you can do doping. So after doping two types of semiconductor, we get N type and P type. N type we will get when we will add pentavalent impurity. P type we will get when we will add trivalent impurity. So after that we will discuss N type semiconductor. What are N type semiconductor?
Sir,
So
pentavalent means?
pentavalent means the impurity which is having 5 valence electron.
Okay.
Trivalent impurity
Three.
means,
Okay. Three.
yeah. So I will discuss this later. Means
Okay.
when we will discuss the N type, then I will tell you there what is the meaning of pentavalent. So pentavalent impurity N type. So pentavalent impurity atom like phosphorus, antimony, indium replaces silicon or germanium atoms in a crystal.
Yeah.
So basically, this is the silicon crystal.
Yeah.
So you are adding pentavalent impurity. Suppose you have added phosphorus. So few atoms of silicon will be replaced by phosphorus like this. In more clear way, you can see this. So basically, silicon is having 4 valence electron. Phosphorus is pentavalent impurity having 5 valence electron. So when you will add the pentavalent impurity, silicon's atom will be replaced by the phosphorus atom. So this phosphorus atom is having 5 valence electron. 1, 2,
Yeah.
3, 4, 5.
Mm.
So 4 of the electrons of phosphorus will make the covalent bond with the silicon. There will be one free electron. And this
Okay.
free electron will be nearly free electron because
Okay.
this is not completely free electron, because there will be some influence on this electron
Yeah.
of the nucleus of the silicon, and this silicon, and this phosphorus, you can also say. So now this is very theoretical part. 4 out of 5 valence electron of phosphorus forms covalent bond with the neighboring silicon.
Yeah.
1, 2, 3,
Yes.
4. They
Yeah.
are forming the covalent bond. Just a minute. This phosphorus is having 5 valence electron. 1, 2, 3, 4, 5.
Yeah.
4 valence electron of phosphorus making 4 covalent bonds with silicon. One is free electron. This is nearly free.
Yeah.
You will give small amount of energy, this will become free electrons.
Okay.
So 4 out of 5 valence electron of phosphorus forms covalent bond with neighboring silicon atom. Sorry. But fifth electron is nearly free, as I told you.
Yeah.
So nearly free, okay?
Yeah.
So the ionization energy required to free fifth electron is very low. This is the ionization energy, means this much energy you have to give so that this electron will become free, and this energy will be available at room temperature. Okay. And this energy is very less as compared in case of the semiconductors, intrinsic semiconductor. To make an electron free, more amount of energy is required, and that energy is this, and this is more than this. So you can see in pure semiconductor, energy is required to break covalent bonds to free electron is, for germanium it is 0.72 electron volt, and for silicon it is 1.1 electron volt. And this energy is not available at room temperature. This energy is available at room temperature. We will see in the next. The energy required to free fifth valence electron can be obtained at room temperature. So this electron is set to free and it goes to the conduction band and is available for the electrical conductivity. Okay. Now fourth point, pentavalent impurity donates 1 electron per atom. This is the pentavalent impurity, phosphorus. This is donating 1 electron, 1 free electron, or you can say 1 nearly free electron it is donating.
Yes.
So pentavalent impurity donates 1 electron per atom, and hence they are called donor impurity. So pentavalent impurity are called donor impurity. Okay, the conductivity increases with doping. More doping you will do,
Yeah.
more donor impurity you will add, more free electron you will get, more will be the conductivity. I told you that at room temperature, some of the covalent bonds can break, and due to that, electrons and holes are created.
Yeah.
In case of the intrinsic semiconductor. So
Yes.
some free electrons are also generated due to breaking of few covalent bonds, and equal number of holes are also generated.
Okay.
Ne is the number of free electrons per unit volume. NH is the number of holes per unit volume. So Ne is the number of electrons. So from where we are getting electrons? We are getting free electrons from the pentavalent impurity or due to breaking of covalent bond. So almost 90% we are getting by the pentavalent impurity, almost 10% we are getting due to breaking of covalent bond. Holes we are getting only due to breaking of covalent bond. So electron will be much more as compared to the hole in case of n-type semiconductor. So the majority charge carrier in n-type are electrons. Okay.
Okay.
So 8th point, n-type semiconductors are electrically neutral. So why they are electrically neutral? When you are adding phosphorus, this phosphorus is having 15 proton and 15 electron. That is why this is neutral. It is giving 1 free electron, but along with it will give 1 free proton also, 1 extra proton also it will give. So pentavalent impurity brings 1 extra electron, but it also brings 1 extra proton. Now see the energy band for n-type, conduction valence band, conduction band. So in conduction band, for n-type semiconductors, these are the free electrons in conduction band, donated by the impurity. Okay, and basically this is the donor level. Donor level means this amount of energy you have to give to the donor level is the energy level of the free electron, you can say. So this amount of energy you have to give to the uh, electron given by the impurity so that it can move to the conduction band, and this value is very very less. Okay,
Okay.
and this hole is created at the room temperature due to breaking of the covalent bond. So basically, majority charge carrier in case of the n-type semiconductors are holes. Oh, sorry, free electrons.
Yeah, see it.
Free electrons. This energy gap is 0.72 for germanium and 0.1 for silicon. So this is a donor level. Donor level means this is basically energy level of the electron. A small amount of energy you will get give to the electron. Electron will move to the conduction band and responsible for the electrical conductivity of n-type semiconductor. So electrons are majority charge carrier, holes are minority charge carriers. So one by one you should take the screenshot, then we will discuss the next topic.
Okay, sir. Done, sir. Sir, can you show third point? Yeah. You're done, sir. Done, sir.
So extrinsic semiconductor is done. Now doping.
Done, sir. Done, sir.
Just wait. After this diagram, you should, when you will revise now,
Yeah.
after this diagram, you should see this diagram.
Okay.
And after this diagram, you should see this diagram.
All right.
So arranged manner I have made.
Okay. Done, sir.
Now take. Okay.
Done. Done, sir. Done, sir. Done, sir. Done, sir. Done, sir. Sir, can you show the last paragraph? Yeah. We're done, sir. Sir, can you just show the n-type one? Yeah. Yes.
Okay, I'm just zooming it
Yeah.
out,
Yeah.
then
Yeah.
we'll find.
Yeah. You're done, sir.
Okay, so now I think zoom in is required.
Yeah. Done, sir.
So electrons are majority charge carrier, holes are minority charge carrier in n-type
Yeah.
semiconductors.
Yes.
So in p-type semiconductors, what will happen? holes will be majority charge carrier, and the electrical conductivity of p-type semiconductor will be due to majority due to hole.
Yeah.
So now we will discuss p-type.
Mm.
So when n-type is completed, so after that p-type will become very easy for us. So p-type. So p-type, I told you, we will add trivalent impurity atoms. Trivalent impurity atoms are those atoms having 3 valence electrons, like boron, aluminium, indium, and these atoms will replaces the atom of pure silicon or germanium in crystal. So this is the electronic configuration you can see. Aluminium, and someone can ask, okay, while you are doping for silicon, why you are using aluminium, not boron, not indium? See the atomic number of aluminium and silicon, almost difference of 1. So the size of aluminium and silicon is almost same. So that is why we are adding aluminium as an impurity.
Okay.
Now, these diagrams are very important. So first analyze this diagram. So in this diagram, this +4 is representing, this +4 is, I have written now like this, +4, and this circle.
Yes.
This is representing silicon.
Okay.
And this +3 now is representing aluminium.
Okay.
So basically, why I took this diagram, because I want that you should know what is happening, because here earlier they are all, earlier this was the diagram. All silicon atoms are there.
Yeah.
So we can add this diagram also. So in this diagram, this is the diagram, and what you are doing, you are adding trivalent impurity.
Yeah.
And which trivalent impurity you are adding on the means with silicon, you are adding aluminium.
Yeah.
Having 3 valency electrons.
Yes.
So when you will add, it will become like this. Aluminium, sorry, silicon, and one of the silicon is replaced by aluminium.
Okay.
Mechanism, here you will see. Aluminium is having 3 valence electron, 1, 2, 3. All these 3 valence electron will make covalent bond with another silicon atom, but there will be, this aluminium is having 3 valence electron.
Yeah.
So 3 covalent bond made, but there will be one hole, because this aluminium is having only 3 valence electron, na?
Yeah.
So due to this aluminium having 3 valence electron, all the 3 valence electron will make covalent bond with other silicon, with neighboring silicon atom, and there will be one hole due to this trivalent impurity, because here there is one vacancy. This is the vacancy basically.
Yeah.
So due to the trivalent impurity, one vacancy is created, and basically this is an incomplete covalent bond, because aluminium is not having the electron to complete this bond. So here a vacancy is there, means an electron can go in this vacancy. So by trivalent impurity, what we are getting? We are getting one free vacancy or hole. Now this is theory. 3 valence electron of aluminium forms 3 covalent bond. 3 valence electron of aluminium forming 3 covalent bond. 1, 2, 3. They are forming 3 covalent bond.
Yes.
Okay. With neighboring silicon atom, a vacancy is left at one side of trivalent impurity atom. This is the vacancy left. Okay. On application of the electric field, an electron from covalent bond may jump to the hole and a new hole appears at the site of electron. So what will happen? Hole is already there. Hole is already there in this. When you added aluminium, holes will be already there. So what will happen? This hole will be occupied by the electron when you will apply a small electric field. Okay. So on application of electric field, an electron from one covalent bond may jump to the hole and new hole appears at the site of electron. So basically this is the hole. When you will apply the electric field, this is the aluminium. Aluminium is creating one hole. So this hole will be occupied by this electron, neighboring electron, when you will apply the electric field. This requires very small amount of energy. Basically, to move the electron from here to here, a small amount of energy is required, and data is given here. This energy is available at room temperature, hence large number of holes are available for electrical conduction. So in this way, the holes will be created. Motion of the holes will be there. Understanding why the holes are creating. Holes are creating because holes are creating because this aluminium is accepting one electron. So here a vacancy is created. This is the new vacancy. So trivalent impurity, what the trivalent impurity? This aluminium, what this aluminium is doing? Accepting the electron. Accepting one electron. So these impurities are accepting type impurity or acceptor impurity. Trivalent impurity accepts an electron from neighboring atom, hence it is called acceptor impurity. Number 5. So electrical conductivity depends upon the level of doping, more acceptor impurity and more holes. I told you earlier also. Few covalent, now again this will be at room temperature, so few covalent bond will break, electron will become free, and holes and electron will be generated. So few covalent bonds may break, which generates free electrons. And equal number of holes will be there. I told you, na? Number of holes will be due to trivalent impurity and due to breaking of covalent bond. So number of holes due to trivalent impurity is giving one hole. Indirectly you can say, and some of the breaking of covalent bond will also give one hole, but 90% of the hole you will get from the trivalent impurity. Only 10% holes you will get by breaking of covalent bond, and electrons you are getting only by breaking of covalent bond. So number of holes are much more greater than the number of electron in case of the p-type semiconductors. So holes are majority charge carriers. Now energy band diagram is very simple. Energy band diagram, valence band, conduction band. Now less number of free electrons are there, so in conduction band there will be less number of free electrons, but there are more number of holes, so more number of holes are there in, and holes will be in the valence band. Okay, and this is the acceptor level. Acceptor level means this level is representing the energy of the electron, bonded electron, energy of the bonded electron. So that the bonded electron will move to hole or will occupy the hole. Okay. So this is the acceptor level. If you will give this amount of energy available, then electron will move to the hole and new holes will be generated. In this way, the holes will be generated by a small amount of energy adding.
Alright.
So please take the screenshot.
Done. Done. Yeah, done.
After that, this diagram is there.
Hmm. Done. Yeah, done.
Okay, just a minute. First, take the screenshot of this. After
Okay.
that.
Done.
Take this.
Yeah, done. Done.
So basically, this topic is purity theoretical topic.
Hmm. Done.
Now you should take a screenshot of this energy band.
Yeah. Done.
Okay. So after this, we will discuss the PN junction
Okay.
diode.
Yeah.
So PN junction diode is nothing but an intrinsic semiconductor is taken. One
Yeah.
side of that means half of that portion is doped with P type semiconductor,
Yeah.
and
And
half
yeah.
of that
Yeah.
is doped with N type semiconductor.
Yes.
We know that in P type semiconductor, holes are majority charge carrier.
Yeah. And
In N type
electrons and
semiconductor,
yeah.
electrons are majority charge carrier.
Minority. Yeah.
Electrons are majority charge carrier in P type semiconductor, N type semiconductor.
Yeah.
So what will happen? Here, this side holes
Yeah.
will be, if you are taking N type semiconductor, this P type semiconductor this side, N
Yeah.
type semiconductor this side.
Yeah.
More electrons, more holes. So
Yeah.
concentration difference will be there. So
Yes.
there will be the drift of electron and drift
Yeah.
of hole.
Drift. Yeah.
And after that, they will cross the junction, and
Yeah.
that is known as the diffusion. Drift and
Yeah.
diffusion will
Diffusion
takes
current.
place due to the concentration. And
Yeah.
after that, what will happen? A depletion layer will form, and depletion layer we will see what is the depletion layer. Depletion layer contains the immobile positive and negatively charged ion. Positive charge ion will be on N side, negatively charged ion will be on P side. I will tell you why.
Okay.
And there a potential barrier is will be created after some time, and after that there will be no further motion of the majority charge carrier. Okay,
Yeah.
so we will discuss this.
Yes. Okay.
So PN junction is very simple. This is PN junction diode. So you have taken a silicon crystal, this whole silicon crystal you have taken.
Yes.
One side is P type, one side is duped. This is P type, and this is P type semiconductor, this is N
Yeah.
type
Yeah.
semiconductor. This
Enter.
is like this. You are adding P type and N type semiconductor like this. This
Yeah.
is
Yeah.
P type semiconductor, N type semiconductor.
Yeah.
Add it,
Yeah.
sorry, join like this.
Yeah.
But you have taken a silicon crystal. Joining is difficult, so that is why we have taken a silicon crystal, doped
Yeah.
one side with P type, doped another side with N type. So basically, this is P type semiconductor, N type semiconductor,
Yeah.
and I have to remove this. So what is happening? Let me tell you. Here, electron, this point is representing electron
Yeah.
holes.
Yeah.
So take one any one side, take N side.
Okay. And yeah.
So what will happen? Concentration of hole here more concentration.
Yeah.
Electrons is having less concentration.
Yes.
Okay. Here the concentration of electron is more and hole concentration is less.
Less. Yeah. It's
So
magnetic.
due to this concentration difference, what will happen? Electron will move from N type to the P type, so
Yeah.
that there will be a balance of concentration on both sides.
Yes.
And holes from P type will move to the N type,
N type. Yeah.
so as to balance the concentration. So let us take the example of N type. So from here electrons are moving from N type, the electrons are moving to P side and holes are moving from P type to N type. So
Yeah.
what will happen when electron will move from N type to P type? When electron will cross the junction, crossing the junction is known as diffusion, and when
Yes.
electron will move within N type, that is known as drift. So
Drift. Yeah.
basically, when electron will move finally from uh, N type to P type, so electron is negatively charged, so electron will leave positive ion. On from here, holes are moving and holes are positively charged. When holes will move from here to here, then
Yeah.
holes will leave here negatively charged ions. Try to understand.
Hmm. Yeah. Okay.
And
Yeah.
these ions are immobile. Immobile means they will
They
not
cannot
move.
move. Yeah.
Why they cannot move? Because there will be a force of attraction between negative and positive charge.
Yes.
And this is the junction. This junction. Have you heard the word railway junction?
Yeah. Yeah. Yeah.
So that junction means joining. Junction point means when you are joining something,
Yeah.
yeah,
Yeah.
and at the edge of both the object there is a junction.
Yes.
So basically, this is the junction, P type, N type. So now, and this negative and positively charged ion will be in a region, and that region is known as the depletion layer. So basically, this is the depletion layer region. So I have shown here depletion layer.
Hmm.
So after that, there is theory. Okay,
Okay.
theory is very easy. Focus on the theory.
Yeah.
When a single crystal of silicon or
Yeah.
germanium is doped in such a manner, with me, you should also focus on the theory.
Okay.
When a single crystal of silicon or germanium is doped in such a manner that half portion of it acts as p-type, other half portion of it acts as n-type semiconductor, this
Yeah.
device is known as the p-n junction diode. So this is clear.
Yeah.
After that, the process involves the formation of PN. The process involved in the formation of PN junction are diffusion and drifts. And why they are the diffusion and drifts are taking place due to the concentration difference.
Hmm.
Due to
Concentration.
concentration difference.
Yeah.
Of holes on P side, of holes on N side, of electron on P side.
Yeah.
So due to the concentration difference, the electron will drift from N to P, I told you, leaving behind positive ion. In N type, holes will
Yes.
drift from P to N side and leaving behind negative ion in P
Hmm.
side.
Yeah.
Negative ion, P side, positive ion, N side.
Yeah.
And this will set up a positive and negative ion around the junction, and this layer is known as the depletion layer. So now depletion layer is clear. So this is positive charge, this is negative charge. So due to
Yeah.
this, there will be a potential difference will be created, and that potential difference is known as the potential barrier.
Hmm.
So
Yeah.
it will be like this: negative charge, positive charge. So we can represent it in the form of a cell. So negative charge, positive charge, and the potential difference will be potential barrier.
Yeah.
So you can see, if you will plot the graph of the potential with distance, this is the junction. So
Yeah.
initially the potential will be constant, potential difference will be constant, and near the junction the potential difference will increase. Why? Because suppose you are moving from P to N side. So here
Yeah.
is negative, and after that it is positive. So it will increase. After that it will become constant. Constant, increase, constant. And
Yeah.
this difference, okay, this difference is known as the potential barrier.
Yeah.
This
Potential.
difference,
Yeah.
this difference means the difference of this negative potential and difference of this positive potential is known as the potential barrier.
Yeah.
So what is potential barrier? The accumulation of positive ions in N type and negative ion in P type set up a potential difference across the junction, and this potential difference is called potential barrier. It stops the further deposition of charges. So due to this potential barrier, further
Yeah.
deposition of charges will be stopped. Okay, and potential barrier for the silicon is 0.7 volt, electron volt basically it will be.
Yeah. Okay.
And for germanium, it will be 0.3 electron volt. So now after this, the story is very simple. Due to this potential barrier, due to this potential difference, there will be an electric field. There will be
Yes.
an electric field.
Yeah.
Okay, there will be an electric field, and that electric field will be due to potential. So that is known as the barrier field. So barrier field is the potential difference or potential barrier setup an electric field across the junction, and this field is called barrier field. So barrier field can be calculated by potential barrier divided by length of depletion layer. Now, what is the symbol of PN junction? So symbol of
Yeah.
PN junction diode is this: an
Yeah.
arrow, straight line like this,
Yes.
N side, and this is P side PN junction diode. How many topics left? Okay, so take the screenshots.
Done. Yes, it's been scroll a little bit up. Yeah. Done. Done.
So, Ziyad, there is a requirement of one more class.
Yeah. Okay.
So somehow we have to manage that.
Yeah. So can you show me
On
the first point?
y-
Yeah, this one.
yeah, of course, of course. First point means this one,
No, no, the
this,
yeah,
this.
yes. Yeah. Done. Yeah, done. Done.
Just a minute. First, take this screenshot.
Okay. Done. Done. Done.
Oh. Okay, Ziyad. So, can you join on Saturday?
Yeah. Yes, I'll be able to join.
Yeah. If you will join on Saturday, so Saturday, inshallah, I will finish this because now, because not to explain these topics like what
Yeah.
is energy band, what is intrinsic and extrinsic semiconductor, or
Yeah.
everyone know. Just a minute, Azan time is there, so
Okay.
then I will tell you.
Okay.
Hmm. So actually, what happens, na, everyone knows what is intrinsic semiconductor, what is extrinsic semiconductor, what is basically energy band also. But the depth, they do not have the depth of that concept.
Yeah.
What is happening inside the extrinsic semiconductor, what is happening inside the p-type semiconductor, why in p-type semiconductor holes are majority charge carrier, why in n-type semiconductor electrons are majority charge carrier, okay,
Yeah.
why on 0 Kelvin the intrinsic semiconductor behaves as insulator. So
Yes.
I tried in this presentation, you can say, or in this class, I tried that all these answers of all these answer of these questions you should get. So basically, this is the main purpose of the class. Okay.
Yeah.
Definition extrinsic semiconductor, you can say when doped semiconductor is extrinsic semiconductor. But what is the mechanism of that is to explain that is difficult for me also, because basically what we are doing now, we are studying the micro level. Okay, we
Yeah.
are we are going into the atom